Here you go. Whoop. Let me. I feel like an animatronic man with all these cords hanging off of me. Okay. Anybody else on this table? What about this table? Okay, you guys got them. You need one, Skyan? Okay, this table, you guys, two? Okay. Here, I think there's an extra one there. Here you go. What about for you guys? You guys have an evaluation yet? Okay, so here. Okay, so we will go ahead and get started. So this is the final exam review for Chemistry 2. Who here is in Hampton's class? Can I see hands? Okay, so pretty much everybody. I thought that would be the case. One professor already had their final exam, so none of the students will be here for that. Okay, so this review is going to go for 2 hours. It's going to be from right now until 4. I'm going to leave about 10 minutes of questions at the end, just so that if you guys have any, we can go over them. Also, if you guys want to access the review sheet I'm going over, it's on this link right over here, ucfstudyunion.wordpress.com. And after this review is over, if you go to the UCF SARC YouTube page, you can find a recording of this review online, and that'll be up really forever. So anytime this week, you can just go back and watch that video. While I'm doing the review, my back is turned to most of you guys, so don't raise your hand. It's not going to work. Even if you're in front of me, don't raise your hand. Just call out my name. Say, hey, Tim, or you just shout out your question, okay? And if we're getting too many questions, I'll just let you guys know that we're going to hold back for a little bit so we can keep moving through the review. A quick thing about this review. This review has about 5 questions from each chapter that I felt like were the most important questions. I'm not going to be able to go over every single question, but my plan is to, as we're going through every question, if I don't have time to go over it, I'll at least give you the notes that you need to solve that problem. And all the answers for every question is in the back of this review document. So if you go online and you access the document, you can just go to the back, and all the answers are here. Okay? Let me see if there's anything else. Okay, yeah, quick thing. I passed out a bunch of evaluations or surveys. Don't fill those out yet because you guys haven't actually seen me review yet. About halfway through, I'm going to try to remember to ask you guys to fill that out. We're going to take like a mini break, and we're going to go over that. But I'm going to go ahead and get started. If you can't see the question, if the camera angle is weird, just let me know and I will fix it. And again, welcome to everybody who's here and everyone who's watching or who's going to be watching online. So, before we get started, a lot of you guys are coming here because of the ACS, which is the final exam review that everybody in Chem 2 has to take. And a lot of you guys have come to me, a lot of my students have come to me and asked about how to study for it. And every time they ask me, I let them know that the ACS is just a final exam. It's testing you on the stuff you've already learned in Chem 2. Some of the questions can be a little bit different than what you've seen, like they just look a little different, they ask the question a little differently, but at the core, everything is just what you've already learned in Chem 2. So treat it like that. Just remember that if you studied Chem 2, you should be prepared for the ACS. So if you have a good handle on everything you've already studied throughout the semester, you're going to be good for the ACS. Another thing is, it can be kind of hard during any final exam to figure out where the question is coming from. You see a question, you're like, okay, what in the world do I do? As we go through this review, I'm going to try to help you guys find how to solve those kinds of problems. And really the trick is looking at key words. So throughout the review, I'm going to read off the question and ask you guys to help me, and we're going to find keywords that help us point to which kinds of formulas or concepts we're going to be talking about. So as I go through this review, I'm going to be asking a lot of questions. So make sure to keep your minds on. I know it's finals week. A lot of us have had like zero sleep, super stressed. So while you're here, just try to calm yourself down and keep your minds open and ready. As I ask questions, you answer. Okay, so into the first question here. Choose the substance with the highest boiling point. So anytime we see words like boiling point, surface tension, viscosity, vapor pressure, what are some things that should come to mind? Okay, I heard molarity. Anything else? Okay, intermolecular forces. That's right, and I heard like polarity. So that's exactly right, polarity, polar molecules. We have dispersion. Let's see if I can get this focused in a little better. We have dispersion. We have dipole-dipole. We have hydrogen bonding. I'm going to see if I can, there we go. And we have ion dipole. Those are the 4 types of intermolecular forces. And that's what we should think when we see words like boiling point, viscosity, surface tension. So when I ask you about the highest boiling point, what kinds of intermolecular forces am I talking about? Strong ones or weak ones? That's right, strong, because boiling point means that I'm trying to get to a temperature that's high enough to start the substance boiling, which means I'm going to be pulling those molecules kind of apart from each other. Okay, and so so the higher the boiling point, that's going to mean I also have really strong intermolecular forces that are like holding it together and trying to keep it from boiling. So, anytime I look at a problem like this, usually hydrogen bonding is going to be the highest intermolecular force I see. We do have ion dipole, but this involves 2 things. It involves a polar compound, and it involves some kind of ionic compound. So unless you see 2 pieces, like a salt and a polar solvent, it's not going to be ion dipole. If you see just a bunch of just one substance, it means that hydrogen bonding is really the strongest one we can talk about. So I'm going to start by looking for hydrogen bonding. Do you guys see any molecules in here that have hydrogen bonding? I heard C. Remember, hydrogen bondings, what kinds of bonds do I have to form hydrogen bonding intermolecular forces? That's right, hydrogen, H to O, H to N, or H to F are going to give me hydrogen bonding intermolecular forces. Karina?
What about for the vapor pressure? The weaker the vapor pressure, the higher the vapor pressure, the weaker the intermolecular forces, right?
That's right. So make sure you guys go through and understand viscosity, boiling point, vapor pressure, and how they relate to the intermolecular forces. Karina said the weaker the intermolecular force, the higher the vapor pressure, and that's right. Okay, so, yeah.
What about the viscosity and surface tension?
So I'm going to move on for now to the next question, but I'll let you guys look on your own at the other ones, okay? So for the next question, calculate the mass of water that can be vaporized with 150 kilojoules of heat at 100 degrees Celsius. So we're trying to find the mass of water that can be vaporized. And we're given a bunch of numbers. So it's clear we're going to have to use some kind of equation or formula. Any thoughts on which one? I think I hear some people whispering it. Feel free to shout it out. It's okay if you're wrong. I'll help you out. Okay, that's right. It's the QMCAT one. Okay, but remember, QMCAT deals with when the temperature is being raised. There's another one that's similar that deals with a phase change, like vaporization, fusion, or melting. What's that one? Not Q equals MCAT. That's right. Q equals N times delta H. Okay, and so here I'm going to, if I'm looking for mass, that means I'm going to be solving for probably the moles here. So I'm going to rewrite this as Q over delta H. I'm going to plug in those numbers. I had 155 kilojoules. Can you guys see okay? I know it's a little cramped right now. And delta H was 40.7 kilojoules per mole. And when I solve that out, I'm going to get here 3.81 moles. Okay, and remember I'm trying to get the mass of water. Right now I have the moles of water. How do I go from moles to mass? That's right, molar mass. And so here, I'm going to take my moles, 3.81, and I'm going to multiply it by the molar mass of water, which is 18.02 grams per mole. And that's going to give me 68.6 grams, which is D. Okay, I'm going to move on to the next one now. Okay, so the ACS is going to have charts in it that you guys probably haven't really focused on. So make sure to look back at the charts in the textbook and just make sure you understand what they are and what they're talking about. So here we have a phase diagram. The question is, what is the substance at 30 degrees Celsius and 1 atmosphere? So for this, and it says use the diagram above to answer problems 3 through 4. So here, 30 degrees Celsius, I see the temperature on the x-axis, so I'm going to here mark this. And 1 atmosphere, so that is right over here. And I'm going to trace to make the lines match on the graph. And it's asking me what is the substance at that temperature and pressure. And they're asking about like crystal, liquid, solid, or gas. So any thoughts about what this is? I heard C. Why C? That's right. When you look at a phase diagram, it goes solid to liquid to gas. Okay, and if you look here, I have a lot of charts and equations included in the review. So here, solid to liquid to gas. And so the understanding is that you have to know where the solid, liquid, and gas are found in a phase diagram. And so liquid is the answer. The next question is, what does line segment AD represent? And so here I'm going to look back at the phase diagram, and I'm going to look for line segment AD. And that is right over here, A to D. What phase change is happening going across this line segment? I heard E, so I heard fusion. What's another name for fusion? Melting, that's one that we're probably more familiar with. So if you think about it, solid to liquid, that's the transformation happening across line AD, which means that, think about it, solid to liquid, that's melting, and the other word for that is fusion. So that makes line AD the fusion curve. And make sure to look back at phase diagrams and understand which curves are what: fusion, sublimation, vaporization, and also things like triple point and critical point and what they mean. Yes, Karina?
Before we go on, what was Q equals MCAT again?
We're actually going to get to another problem, actually this problem here, which talks about it a little more. So I'm going to answer your question probably by going over problem number 5. Okay. So here this question says, how much heat in kilojoules is needed to raise the temperature of a 12-gram benzene sample from negative 10 degrees Celsius to 25 degrees Celsius? So how much heat is needed to go from one temperature to another? What kinds of questions did we see that talked about that? You don't have to raise your hand, just shout it out.
The melting curve for like water, like the melting diagram.
That's right, melting diagram. Another name for that is like heat curves.
Yeah.
So we could think of the heat curves of a substance. And every substance is going to have the same kind of general layout for a heat curve. Okay, here I have time. And here I have temperature. Okay, so starting out here, I have a solid, and I'm going to raise the temperature until I'm going to get to a point where that solid's going to start melting. And then the temperature is going to stay the same while that solid is melting. And when it's finished melting, here, what do I have now once it's finished melting? A liquid, perfect. So now that it finished its phase change, it's going to start heating up again, heating up, and then it's going to start, what do liquids do? Vaporize. Can I hear it again? I hear a lot of you answering very quietly. What do liquids do? What phase change do they do when you're increasing temperature? Vaporization. Don't worry, I'll work on you guys to get a little louder. So vaporization. So it's going to start vaporizing until we get to a gas. This is what the heat curve looks like. And so what we need to do is, for this problem, we need to figure out what the phase is that benzene is starting at. Here we're at negative 10 degrees Celsius going up to 25 degrees Celsius. So we need to figure out what is the phase that benzene is starting at. Does anybody know negative 10 degrees Celsius, what phase is benzene in? Why solid? Okay, that's pretty cold. That's a good assumption. It's a really cold temperature, so it's probably a solid. But do you guys have to memorize the melting point and boiling point of every single substance that there is? No, only one substance, and that is what? Water. You need to know that the melting point for water is what? I'm saying in Celsius. 0, perfect. Don't raise your hand, just shout it out. And what is the boiling point for water? 100. You need to know that. Otherwise, they're going to give you here what the melting point is and what the boiling point is of the substance, unless it's water, okay? So if you look here, the melting point is 5.5 degrees Celsius.
What's the melting point again?
Right, oh, for water, 0. Here, negative 10 is less than the melting point, so that means it's a solid. So I'm going to mark here, solid. And now I need to look at what the phase is at 25 degrees Celsius. Can you guys tell me, looking at this diagram, what the phase is, or looking at the numbers? Liquid, that's right. Because it's after the melting point, so it became a liquid, and then it's before the boiling point. If it was past the boiling point, what would it be? Okay, I'm going to ask that again. I heard a lot of you guys say it, but not loud enough. If it's past the boiling point, what would it be? Perfect, a gas. Okay, so that means we're right about here. And remember that we talked about there being two equations, Q equals MCAT and Q equals N times delta H, for calculating phase changes and increases in temperature for a substance. So here, I'm first going to have to calculate the temperature the amount of energy it takes to raise the temperature of the solid from here up to the melting point. Then I'm going to have to calculate the amount of energy it takes to melt that solid into a liquid. And then, once it's a liquid, I'm going to have to calculate how much energy it's going to take to raise the temperature of that liquid. So that's a third step. Okay, and so for the first step here, I'm going to be using Q equals M cat. Okay? And that's because it's raising the temperature. If it was the phase change, it would be Q equals N times delta H. I'm going to go ahead and show you guys what this looks like worked out, and I'm going to walk it over with you. So, here we have the Q equals the MCAT. M is our mass, which is the 12 grams of benzene. Our specific heat When we look through, we need to make sure we find the correct one. Here we have the specific heat of a solid, the specific heat of a liquid, and that's it. So which one do we need, the liquid or the solid one in the first step? The solid. That's because we talked about it being a solid. Okay? So we plug that in, and then this is the really tricky part that a lot of people get messed up on. The change in temperature is not the change from the beginning to the end. That change in temperature is just the change for this initial step from negative 10 degrees Celsius up to the melting point, which is here 5.5 degrees Celsius. And so here 5.5, which is the final, minus negative 10 is going to give us our delta T. And here when I plug all those in and convert it to kilojoules, this is what I get. For the second step, we're talking about a phase change, which means we're using Q equals N times delta H. Here, when you use the molar mass, multiply it by the grams, you're going to get the moles, which is 0.15 moles. And you just multiply it by the delta H here. And you have to make sure that you have the right heat, not the heat of, did I give you any others? Yes, so I gave you the heat of fusion, but sometimes they might give you the heat of vaporization as well. Just make sure that you know that because we're going from a solid to a liquid, that this is talking about fusion or melting. This is not vaporization. So just make sure you have the correct delta H. Did you have a question?
So for the moles in the second step, you got that from the grams they gave you and then the molar mass they gave you as well?
Okay, so that's exactly right. The question was, where did I get the moles in the second step? And that's from the 12 grams, the mass they gave me, and it's from the, did I give you guys the molar mass? Yeah, the molar mass of benzene. You might not be given the molar mass, and you might have to calculate it, but here benzene, you're not given the chemical formula, so you're not expected to have it like memorized or know what benzene is. You might, though, have to calculate the molar mass. So if they give you a chemical formula, make sure you guys remember back from Chem 1 how to get the molar mass. But I will say, usually on the ACS, they don't want you to waste time doing that, so they just give it to you. But if they don't, just make sure you remember how. Okay, the last step is after melting, going up, increasing the temperature up to 25. So that's again Q equals MCAT. So here I'm replugging in my 12 grams of benzene. It's still 12 grams, it hasn't changed. Now I'm using my specific heat of a liquid, because now I'm a liquid, and I'm doing my delta T for up to 25 as a final, minus the initial, which was our 5.5. Okay? And then I solve for that and add all the heats together to get the answer of B here. Now, I know a lot of you guys are thinking this is like a super long problem, and it really is. So, on your ACS, you're probably not going to have something that's 3 steps. If anything, at the very most 2 steps. Usually, though, 1 step, just like the first problem, just like number 2 that we did. It was just a single step. So make sure you guys can do up to 2 steps, really. But 3 steps, this is just to make sure you guys really understand it. But it's a little overkill for the ACS. Okay, I'm not going to show you this answer sheet. Now I'm going to go back to the other sheet here. Which of the following substances is more likely to dissolve in CBr4? So when we see the word dissolve, what kinds of terms or concepts do we need to think about? Okay, polar and nonpolar. Okay, there's another kind of phrase that sums that up. It says, no, I'm saying the phrase, it's like dissolves like, okay? Which means that polar compounds like to dissolve other polar compounds, and nonpolar compounds dissolve nonpolar compounds. Yep, and so we need to find out what CBr4 is. Is it polar or is it nonpolar? And it can be a little tricky here. I'm going to draw it out for you guys. Because, remember, polarity talks about one substance being more electronegative than another. So if we look at the periodic table and look at the electronegativity rules, and I'm going to really quickly show you guys what that looks like. If this is the periodic table, electronegativity increases going up and to the right. So if we look at the table, or if the periodic table, Br is more electronegative than carbon. So if I'm going to draw a polar arrow, it's going to be from carbon to Br. And I'm going to do that for every bond here. Okay, so you might think that because there are dipole arrows, this compound is polar. But we have to consider the fact that here we have dipole arrows pointing in the opposite direction. What's going to happen to those? They'll cancel out. That's right. So I'm going to cancel those out. And also up and down, I'm going to cancel those out. Are there any leftover dipole arrows? So is this compound polar or nonpolar? Perfect. So nonpolar. Yes, Karina.
I found out like you can also determine the polarity of like a substance if it has like unequal valence electron sharing between molecules. If it's constant and polar, if there's a lone pair on a central atom.
That's right. You can do it other ways, but I'm just showing you guys an easy way right now. So now I'm going to look for nonpolar compounds, and if you guys look through these, CF4 is a very similar structure to CBr4, and when we draw it out, it's going to have the same kind of effect. We're going to have a bunch of fluorines here, and they're all going to cancel each other out with the dipole arrows. So CF4 is the only other nonpolar compound. Okay, here for this question, number 7. It says the solubility of carbon dioxide gas at 25 degrees Celsius and 1 atmosphere is 6.8 times 10 to the negative 4 moles per liter. So looking at that problem, if you see the word solubility of gas, what kinds of things does that bring up?
It decreases as temperature goes up.
Well, that is an important concept, but I'm saying equation-wise. And I heard someone say it was Henry's law. And that says that the solubility of gas, S gas, is equal to Henry's constant times the pressure of the gas. And here, it actually gives us the solubility of gas at 1 atmosphere. And yeah,
I think I forgot to give you like one of the review sheets.
that's okay. Maybe I'll hand them out to you in just a moment, about halfway through, okay? Okay, so S gas equals Henry's constant times the pressure of gas. And we're told what the pressure of gas is and what the solubility is. The only thing we're not given is KH. And then the second part is if the partial pressure of gas is 0.76, what is the concentration of dissolved gas? So in the first problem, we're given everything but KH. And it's a constant, which means will it change if I do a different problem? No, it's always going to be the same for carbon dioxide gas. So I'm going to solve for my KH, and that's going to be S gas over P gas. Here, I'm just going to plug in the 6.8 times 10 to the negative 4 moles per liter over the pressure of gas, which was 1 atmosphere. And when I solve this out, I got, let me see, oh, it's just going to be the same thing because it's divided by 1. So 6.8 times 10 to the negative 4 is our KH. Now I'm looking for the solubility of, or the concentration of dissolved gas if I have a different pressure. So what I'm going to do is I'm going to plug in my KH that I just solved for, and I'm going to multiply it by my new pressure of gas, which is 0.76 atmospheres. Okay? And when I do this out, it's going to give me 5.2 times 10 to the negative 4, which is D. Again, guys, if you miss any of the answer choices, I have all the answers on the back, and the review, again, can be found right over here at the ucfstudyunion.wordpress site. Also, again, you can find this review on the YouTube page of UCF SARC. So you can actually find me going over this review right now, later on after the session. So if you miss anything, that's okay. Just know you guys can go back to there. For this question, calculate the molality of a solution made by dissolving a certain amount of NH3 in a certain amount of solution. So this question is talking about molality. So we need to remember for this that molality is equal to the moles of solute over the kilograms of solvent. And for this problem, I'm going to show you guys something special. This is a tricky question because they give us the grams of solution right over here. But they don't give us the grams or the kilograms of solvent, which is what we need. So we actually need to use the grams of solution and the grams of solute they gave us to solve for the grams of solvent. And when we do that, we can convert it to kilograms and then plug it in here over the moles. And we can get the moles of solute by taking the grams of solute and multiplying it by the molar mass. Okay? So moles over kilograms, just make sure you don't miss it. You need to solve for the kilograms of solvent. If you guys did this problem before, it's a little, when I worked it out, it works. It still gives you the right answer, even if you don't solve for the kilograms of solvent. That shouldn't be right. It should give you the wrong answer. Just know for the ACS, it's going to give you the wrong answer if you don't solve for that. So make sure that you remember that it's kilograms of solvent, and don't just put in the grams or kilograms of solution. That's the important thing to remember. Give me just one moment, Karina. I'm going to wait for questions a little bit so I can get through a few more problems, okay? So here, I included a table with a bunch of concentrations that you guys need to know. Molarity, molality, and mole fraction are the most important by far. So make sure you know really those top three as the most important ones. And these might show up as well, so make sure you know the other ones too. I'm going to show you guys this worked out because I don't want to spend the time working it out so we can save a little time. Here, for this problem, it says that we have a certain molality of compound Y, and it has a boiling point of 101.3. I'm going to really quickly take the other sheets so we don't have the answers yet. Okay, and it says, which one of the following could be compound Y? The boiling point elevation constant for water is that. So, it's asking which compound could be compound Y. It doesn't tell us anything about what it is. And that's our goal. We're trying to find out what it is. So, if you're just looking at this problem and you just try to think of how to find the compound without breaking down the problem by keywords, you're probably not going to get very far. This is a really good example of when you really need to be thoughtful about what keywords you're seeing in the problem. What's one keyword that's going to tell us maybe an equation to use in this problem? Boiling point. That's exactly right. Do we have any formulas for boiling point? Yeah, we do. And it is this formula right here. Delta TB equals the molality times the boiling point elevation constant times I. A lot of people are going to forget that I value or forget that I is even a thing. This is actually the most important part of the equation, I, and this is actually a question that I had from the ACS. So make sure you guys really know that this is really important that you don't forget that I, or the Van't Hoff factor, is a part of every single colligative property equation, which means freezing point, boiling point. What's another one? Colligative property equation. Not melting. It's, yeah, you don't have to raise your hand, Karina. Just go ahead and shout it out if you remember.
Vapor pressure and
Yeah, vapor.
point.
Freezing point, vapor pressure, boiling point, and what? Not viscosity, it's osmotic. Perfect. Osmotic pressure. Every single one has an I in it. So make sure you know that I is a Van Hoff factor. And I stands for the number of particles that the compound is going to break down into if we like dissolve it in water. So for example, NaCl, which is going to be our answer, I'll show you how. If I put NaCl in water, how many pieces is it going to break into? Two pieces, Na and Cl. So what's the Van Hoff factor for NaCl? It's that simple, okay? So make sure you guys can find the Van Hoff factor for any one of these compounds. Don't forget that if it's not an ionic compound like this, it is just 1. The Van Hoff factor is just 1. So make sure that here we don't forget I, and when I plug everything in, I plug in my change in temperature, my molality, and my Kb. I'm going to solve for I. I'm going to get 2. And then I just need to search through and see which of these compounds has a Van Hoff factor of 2. This is a really tricky problem that could show up in the ACS. So make sure you guys understand Van Hoff factors. And again, I'm going to show you this problem here. I'm not going to show you everything that's solved out, but keywords here, osmotic pressure. So if you see something that's going to point to an equation, don't wait. Write down that equation right away, because that's the first step in solving the problem. And then try to see, how do I move to the next step from here? Karina, yes?
Can I please get one of those review sheets?
Yes, let me pass you one.
Please go over like number 7 and number 8 again, because
So I'm not going to go over any problems I already did, but I will say, Karina, that if you want to look back at the video of this review, you can find me going over that again afterward.
I
Also, if
just want to look at like the worked out thing, okay?
okay, well, if you come to me afterward, I can show you it, okay? So just don't forget to stop by and I'll show you the worked out stuff. So for this problem, osmotic pressure, here's the formula. If you can see here, I crossed out the I. That's because they tell me that it's lysozyme. Do you guys know what lysozyme looks like? No, that's good because you don't have to. If it just says something like lysozyme, benzene, you can assume that you don't need to know what the Van Hoff factor is because you don't have the compound. You can't see what it's going to break down into. So if you see things like lysozyme, benzene, some kind of formula name and not the actual chemical formula written out, then you can just assume that it's not going to matter. So you just take out I right away. And here I'm solving for molar mass. So I solve for molarity first, and I get the moles over liters, and then I just multiply by the liters to just isolate molarity, and molar mass is grams per mole. So I take the grams and put it over the moles. Okay, again, if you guys need to re-see how this looks, go back to the video and just look at what the work is, okay? But I want to keep moving so we get through some of the other important questions. Okay, so this here, for this problem, a 1.26 molar aqueous solution of compound Y, oh wait, sorry, we already did that problem. Let me skip forward. Sorry about that, guys. Here it is. Okay. For the reaction given, NOBR changes from 1 molar to 0.868 molar in the first 10 seconds. Calculate the average rate in the first 10 seconds. This can be a tricky question because average rate is something that Hampton might have just breezed over a little bit, and you guys need to make sure to know it for the ACS and really for Hampton's exam. So remember that average rate, this comes from the chemical kinetics chapter. And rate is defined as the change in concentration over the change in what? I saw people mouthing it. Say it out loud. Say it out loud. Delta T, which is the change in time. Perfect. So, but remember that it's important to pay attention to whether we're finding the average rate of a reactant or a product, and also what the coefficient is. So, for this problem, the average rate is going to be equal to, is NOBR a product or reactant? Reactant. So do I put a negative or a positive? Reactants, you put a negative. Products, you put a positive. So here, negative. Now we need to look at the coefficient. What's the coefficient of NOBR? 2. So I do 1 over the coefficient. And then again, we said it was change in concentration of NOBR over change in time. And so if I solve this out, it's negative 1/2 times, here, the change in concentration, remember, it's final, which is 0.868 molar, minus the initial, which is 1 molar, over the change in time, which is 10 seconds. And when I solve this out, I'm going to get B. Okay, so on to the next question here. Determine the rate law for the reaction here, given the data below. So, here if you look at the answers, I have the general form of rate law. Remember, guys, that rate, the way that you write the rate law is always rate equals K times the concentration of what? Reactants, products, or reactants and products? Which one?
Reactants.
Just reactants. That's exactly right. So this is really helpful to know because look at these answer choices. If I look here, if I see a product in the rate law, I know that that question is wrong. So that answer choice is wrong. So here I have products. So I'm going to take that out. CO2, let's see what else is CO2. Here I see a product. I'm going to take that out. NO. Okay, so it looks like I eliminated all the things with products. So that eliminates 2 answer choices right away. So let's say you totally forgot how to do the problem. If you just remembered that it's just reactants, you would have eliminated 2 out of the 5, which really increases your chances of getting it the right answer. Okay, now I'm going to fill these in, NO2 and CO. And a lot of people are going to get tricked up by this, and they're going to go for the coefficients here as 2 and 2. And they will pick choice A, which is actually incorrect. Because if you remember back when you learned about this, you cannot find these numbers, which are the order of the reactants, unless you have a data table. So don't just look at the coefficients and plug them in for the orders. That would be wrong. Make sure you look at the data table to find what the orders are for these reactants. Okay, so I'm going to really quickly show you guys how to look at these data tables. It shouldn't be heavy on the solving it out. I know some problems you might have done, you had to like calculate it. On the ACS, you can probably assume that the numbers are going to be nice and easy to work with, and you just have to kind of look at it to see how to solve it. So, I have my 2 reactants here, and I need to find 2 trials or experiments where the concentration of one reactant changes, but the concentration of the other one stays the same. This is so that I could see how each reactant affects the rate on its own. I'm not looking at how both reactants are changing at the same time. Just, I'm going to focus in on one reactant changing and how that affects the rate. So here, I have a change from 0.1 to 0.2, which is a doubling, and this stays constant. So when NO2 doubles, how does that affect the rate? Does the rate stay the same? No. If the rate stayed the same, what would that be? What order?
First order.
Not first order, it would be 0 order. Remember, 0 order reactant says that when the concentration changes, it doesn't affect the rate at all. The rate will stay the same, which means 0 order. If the rate doubled, which means that it correlated with the doubling of the concentration, what order would that be? First order, which means there's a direct relationship between the concentration and the rate. The concentration doubles, so the rate doubles. But in this case, when the concentration doubles, the rate what? Quadruples, which means it's to the power of 2 relationship. So doubling times 2 becomes a quadrupling. Okay? And tripling times 3, if you think of 3 raised to the power of 2, what does that become? 9. So make sure you understand that if it instead tripled and it's an order 2 reactant, it would 9 times multiply the rate. Okay, so that's what second order means. But here, it's just doubling and it makes a quadrupling. So I know that NO2 has an order of 2. Now let's look here, 0.1 to 0.2 for CO. And NO doesn't change, so this is the doubling. What happens to the rate? It doesn't change. I know you guys, some of you guys might see, oh, there's a little change there from the 0.002 to the 0.0003, but that's just a sampling error. There's a slight difference in concentration, but that's not like a doubling, that's not a quadrupling, that's pretty much no change, which means what is the order of CO? 0. And anything to the power of 0, what does that become? 1. So I could take it out, and that leaves answer choice B.
So you're looking mostly at the rate, right?
I'm looking, at the concentration doubling, and I'm looking at how that affects the rate. So if it doubled the concentration and that doubles the rate, it's first order. If it makes no change, 0 order. And if it's a 2 times relationship, that's second order. Okay? Yeah? So the question was at what point will we consider it a valid change? So remember that if the reactant concentration doubles in its first order, it'll double the concentration. So if you see that the reactant doubles or triples, and there isn't that same effect on the rate, like a doubling or a tripling, then you can assume it's not a significant change. But they're not going to make it really crazy. It'll pretty much be, on the ACS, it'll probably be no change at all, or you'll see just a teeny change, but it won't be anything significant. Does that answer your question? Okay, great. So for this problem, I'm going to show you guys, it's going to be this is going to be, what are these called again? Do you guys remember the name of this? This is a first order integrated rate law. That was it, integrated rate law. I lost the word. So I don't know how in-depth you guys need to know integrated rate laws for this ACS, but I do know that they give you the equations on the front. So that's 3 equations less that you have to memorize. So don't worry about memorizing them, but you might have to solve for them. Karina, yeah?
Will they give you the integrated rate laws and the units of S?
They would give you the integrated rate laws. They don't give you the units of it would be units of K. They don't give you that. You do have to remember that for 0 order, first order, and second order, there are different units for the rate constant. You need to know what those are just in case it comes up. Okay?
So, ACS will give you the integrated rate laws.
That is right.
Will it give you the half-life?
I do not know anything other than the integrated rate laws. Okay, so, I know, right? So I'm running a little bit behind schedule, so I'm going to show you guys some of the answers to these problems and kind of walk them through with you guys. So for this problem, it says, which of the following statements is false? The reaction is first order in B. Is the reaction first order in B? Actually, yes. Okay, the reason why it's tricky is because here you would expect to see a 1 up here if it was a first order. But there isn't. And remember though, anything to the power of 1 is just that thing. So we don't write a 1, we just leave it there. So this is a super tricky question because this is actually a first order reactant, B. K is the rate constant, is that right? Yep, so that's true. The reaction is second order in A. That is true. There's a 2 up there, which means it's second order. If A is doubled, the reaction rate will increase by a factor of 4. Is that true? Yes, it's second order. So if I double that, it'll quadruple the rate. This is the one that's wrong. The reaction is second order overall. Remember that overall order says you add the reactant orders. That means 2 plus the 1 here, which should be 3, not 2. Okay, and the reason why this is tricky is because you guys might forget that there's a 1 up here, and you might just think that it's 2 plus 0. But it's actually 2 plus 1 to make here third order overall. But this is wrong. It's not second order overall. And for this question here, I'm going to show you guys also the answers. It's all worked out. You have to find the overall reaction. Remember here, what this shows you is called a reaction mechanism. It's where the reaction is written out step by step. And it's different from an overall reaction. Remember, overall reactions, you get that by adding the individual steps up. So this is our overall reaction. Don't forget, guys, that the rate determining step, what is that? Slow or fast?
Slow.
Slow. The rate determining step is the slow step. Don't forget also that you look at the slow reaction reactants to get a rate law. And this is tricky, okay? Pay attention. In a reaction mechanism, we don't need an experiment. We can actually look at the coefficients right here. So 2, that means raise this to the power of 2, and 2 here, that means raise this to the power of 2. That is only in a reaction mechanism when we say step by step. That's different from an overall reaction when we don't have each step written out. Okay, if we just were looking at this reaction, we would not be able to just look at the coefficients. We would need a table, okay? So that's the difference. Catalysts, don't forget, guys, catalysts are used as a reactant and then made as a product. So here, R minus to R minus here, it's a reactant and then it becomes a product. That means it's a catalyst. Intermediates are made as a product and then used up as a reactant later. Okay, so those are different orders. This one is reactant, then product for catalyst, but an intermediate is first product and then reactant. Okay, so make sure you guys can look at a reaction mechanism and get each of those pieces out. Okay, now I'm going to show you guys here. Remember that we can be given a reaction with a particular equilibrium constant. And then we can be given another reaction where it asks us, what is the equilibrium constant of this new reaction? And you get that by here looking at the original and making changes to it until you make it look like the new one. So here, if you look, CO2 is first the reactant, and then in our target, it's a product. So what do I have to do to that reaction to make reactant go to product? What kind of change do I need to make? I need to flip it, that's right. So flip. What is another difference you see between these reactions? Coefficients. You see that in our target, we have a 2 in front of that, and where the 1/2 was, now it's 1. So that means I also need to multiply by 2. And remember that for equilibrium constants, when we flip a reaction, we do 1 over the original K. And when we multiply by something like 2, we raise that to the power of. Okay? And so when I plug in our old one and just do 1 over it and raise it to the power of 2, I get this value here. The other question is when I get the value, the new K of 2.50 times 10 to the 15. Here the question is, what is favored, reactants or products? And can you guys tell me which one is it? I heard, what was that? Products. Can you tell me why? That's right. Bigger numbers, any number greater than 1 is going to favor what? Any number bigger than 1 is going to favor what? I hear some of you guys whispering. Okay, so the answer is products. So I'm going to ask again, and everybody say it together. When the number is greater than 1, we're favoring? Perfect. And when the number is less than 1, we're favoring? That's right. So here, are we favoring reactants or products? Products. And I wrote this wrong. It should be to the power of 5 and not 15. And here it is. Products. Don't worry, guys. I know everybody's sleepy here, okay? I understand. But I'm trying to keep you guys awake so you guys can get everything out of this review session. Yes, Karina.
For the rate, I got, for number 15, I got like rate equals K times HQ2R2 squared because catalyst is not involved in the reaction.
So go ahead, Karina, and talk to me more about it afterward because I want to keep moving on with this, okay? Okay, for this one, we have a reaction, we have a value for K, and we're given the initial concentrations of the reactant. And they're asking me, what is the equilibrium concentration of NO2? Can you guys tell me, how am I going to solve this problem? I'm told about equilibrium, and I'm given the value for K, and I'm given initial, but I'm asked for the equilibrium concentrations. What does that indicate? What kinds of formulas or strategies would I use for this problem? There's like one thing I'm looking for, one word. Ice table, that's it. Don't forget about ice tables, they're super important. Here for this ice table, I wrote up the reaction, and I wrote up my ice table, ICE. Here, they gave me the initial concentration of N2O4, so I plugged it in. They didn't give me anything for NO2, so I assume it's 0. Then here, reactants are negative, products are positive. Because there's a 2 here, I put the 2 here. And then the E section, I just add the 2 together. The tricky part then is this here. So for this problem, remember that I can set up my equilibrium constant expression. Which, remember guys, what do I do to set it up? It's something over something. Products over reactants, that's right. And you raise them to the power of their coefficients. So 2 here, it's a product, so I put it here, raise it to the power of 2. N2O4, here, I have it as a reactant, so it's on the bottom, and it has just to the power of 1, so I leave it as is. Now what I can do is I can plug in the value for K that they gave me, right here, and I can plug in the values in my E row. So my equilibrium row, so 2x here, and for the equilibrium of N2O4, I plug in this here. I'm going to give you guys a little trick here. It's going to save you a ton of time. On the ACS, you can assume that x is always small. You do not have to use the quadratic formula for the ACS. Okay? So every time you have a problem like this, get rid of the x right away and just solve for it that way. Okay? Don't worry about going through the quadratic formula or checking your x. Just go on forward and solve the problem. Here, x, we found the value for x here, and then equilibrium concentration of N2O2, or NO2 is here. So I do 2 times that x, and it gives me this, which is this right here. Okay, make sure you know how to do ice tables, and make sure you don't check for x. Just keep moving forward and take out that x. Assume that x is small. This is another problem that...
Is that 2x or just x?
This is 2x because I'm trying to find the equilibrium concentration of NO2. And if you look, equilibrium of NO2 is right here. And that's 2x. So they might have an answer for just x, like here, but that wouldn't be right because it should be 2x. So make sure you don't get tricked up. A quick note, guys, this is a lot of people hear that the ACS is trying to trick you. Okay, that is partially true. If you do the ACS problems, it's made by the American Chemical Society, which knows what the most common mistakes are that students make. And so what they do is they follow each one of those mistakes and make sure that there is an answer choice that matches with that mistake. So let's say you make a mistake, you might follow it along into a multiple choice answer that matches, but it's the wrong answer. So a lot of people ask me, so what do? I'm panicking now. And the answer is, you make sure you actually know how to do the problems. So make sure to spend time practicing these problems and don't get tricked up with those common pitfalls. If you've come into my tutoring sessions, I've been preparing you guys for the ACS the entire semester. Pretty much every problem we go over, I have told you what the most common pitfalls are. I say, be careful about this, guys. Don't do this. Those are the most common ones that'll give you the wrong answers on the ACS. But if you haven't come to my sessions, don't worry. If you've been practicing chem, or if you practice over the next couple days, you'll be prepared for the ACS. Okay, so don't despair. I just want to let you guys know of the reality so that you guys can prepare accordingly. Again, products over reactants for our K. What are the two types of phases of matter that are not included?
Solids and liquids.
That's exactly right. Solids and liquids. So here I have a solid. Oh, sorry. Here I have a solid. Here I have a liquid. And I can go ahead and cancel them out. I'm not going to include them. And then when I do my products over reactants, I don't have any products because I canceled it out. So I just do 1. And I put it over my only reactant, Br2. And I raise it to the power of 2 because there's a coefficient here. And when I solve it out, this is something you guys are going to want to know. Anytime I have 1 over something with an exponent, like it's in the denominator, I can flip it up to the numerator by changing the sign on my exponent. This is something you probably learned back in college algebra, but it's probably been a while. So on the ACS, this actually tricked me up on a question. Here, just because it's 1 over Br2 doesn't mean that they can't show it like this, and they probably will actually. They'll show it like Br2 to the power of -2. They change the exponent sign to flip it up to the numerator like this. So the answer is this right here. Don't get tricked up by that, okay? Let me see how I'm doing on time. Okay. So I'm going to go through these as well. A quick note about this, guys. Remember that our delta H, if it's negative, it's an exothermic reaction. And we can put the heat as a product in exothermic reactions. And this is important for Le Chatelier's principle, which helps us understand what happens when I change products or reactant concentrations. It tells us which way the reaction is going to shift. So here, for this one, it says which of the following statements is false. So the first thing I did was I saw it was exothermic, and so I put the heat as a product. When it's endothermic, I put the heat as a reactant. Okay, so for this one here, it says which of the following is false. And it says here, adding this gas as the reactant will shift equilibrium to the right. Is that true? That is actually true because when I add a reactant, it's going to increase the reactants and it'll shift over to the products or to the right. The question now says here, ignore this for now. I'll tell you guys about this in a second. but I'm going to say plus heat. Okay, here cooling the container will shift equilibrium to the right. So think about this. If I'm cooling the container, am I adding heat or taking away heat? I'm removing heat, that's right. So I'm taking away a product, which will shift equilibrium toward the products. Okay, so that's true. Adding a catalyst to the mixture has no effect. Is that right? That's right. Remember, catalysts have no effect on equilibrium. They don't shift it either way. And the other question says adding helium to the container has no effect. Is that true? It's true for two reasons. First of all, is helium even in the reaction? No. The other thing is this. Helium is an inert gas. So anytime I have an inert or noble gas, they're not going to affect the equilibrium reaction. Okay? As I'm going through these questions, guys, I'm pulling out a ton of important principles. So make sure you pay attention because that could be a question on your ACS. Yeah, catalysts in noble gases have no effect on equilibrium. That's the statement summed up. The next question says, removing O2, gas from the container, shifts equilibrium to the left. If you look here, I remove O2, which is a reactant. It is going to shift equilibrium to the left because I'm taking away reactant, so it'll shift towards the reactants to replace it. Now, for the last question, adding H2O liquid shifts equilibrium to the left. This is false. Okay, so think about this. Here, if I increase this product, which way should equilibrium shift? It actually, if I increase a product, which way will it shift? It'll actually shift to the left. So why is this wrong? It's a liquid. Do liquids affect equilibrium? No, don't get tricked up by that. So this is false. And so here, liquids and solids don't affect equilibrium. Okay, that's the important thing to remember. For this question, it's very similar. Okay, so try this one as well. I'm going to skip forward to this here. This is looking at salts and finding whether they're acidic, basic, or neutral. Okay, so I'm going to show you guys some really important concepts. I'm going to show you guys a couple statements that should help you understand everything about acidic, basic, and neutral salts. The book is going to go over like tons of statements and you have to memorize like 20 different long statements and it's really difficult. So hopefully if I go ahead and give you a summary of what this means, it's really going to help you. Okay, so be ready. I'm going to write them down. I'd say follow along, write them down with me. Okay, the first statement is that positive ions in a salt, remember we have a positive and a negative piece. Here, the first one is always going to be positive. The second one is always going to be negative. Okay, that's how salts are formed. You always have the positive first, then the negative. And they're always going to have both. The positive ion can always act as a weak acid. And the negative ion can act as a weak, what do you guys think? Base, that's right, weak base. This is a really important statement, so make sure you memorize this. This is very different from what you've seen in the textbook, but this is what they're trying to say in just a couple words. Okay, the other thing is this, that this is always true unless ion comes from strong acid or base. Strong acid or base. I'm going to insert this right over here. Can you guys see that okay? So this is always true unless the ion comes from a strong acid or base. So let me show you what this means. Remember that positive ions always act as what? Acids or bases? Acids. And everybody together, negative ions always act as? Perfect. But the exception was, unless that ion is coming from one of these guys. So here, if we have Cl, Br, I, NO3, ClO4, SO4, these are strong acids. You have to memorize these. Make sure you take time and memorize these. Or if the ion comes from Li, Na, K, Sr, Ca, or Ba, so unless it's one of these ions, then the ion is always called neutral. Let me show you where that's written here, or let me write that down. So unless ion comes from strong, I'm going to say then neutral. I know you guys can't see. Here we go. So unless the ion comes from a strong acid or base, then it's neutral. So tell me here, I'm going to help us practice this out. The question is asking which one of these salts is going to form an acidic solution. So look here, SrCl2. Positive ions always act as weak acids. Negative ions always act as weak bases, right? But are any of these ions coming from strong acids or bases? Is Sr coming from one?
Yeah.
Actually, yes. It's coming from, here, let me show you, SrOH, right over here, SrOH. And then what about Cl? Where's Cl coming from? HCl. So, if those ions are coming from strong acids or bases, what are those ions called? Neutral, that's right. Okay, so here I'm going to cross this out and say neutral and neutral. Here, if I put this salt in a solution, what kind of solution is it going to form? Neutral. That's exactly right. I heard a couple of you guys say it, neutral, because I've got no acidic or basic parts in this salt. So it's going to make a neutral compound, or neutral solution. So, does SrCl form an acidic solution? No. So I only did one of these. You see how many there are? There are 1, 2, 3, 4, 5. I'm not going to do all these 5. I'm just going to show you guys. SrCl, we already said it doesn't. Here or here or here. That leaves only 2 options left. Okay, so try to be really clever about this exam. You guys might be able to save yourself a ton of time. If you get to the point though where you practice enough, you could go through all these salts really quickly. We're really quickly going to do AlBr3. So, oh yeah, so let me first do this one because it'll give us the answer, and then I'm going to do that middle one. Okay, Al, remember, the first thing's always positive, so Al can be what? Acid or base? Acid. Okay, it could be a weak acid. Br, it's negative, so it could be what? Weak base. Now tell me, are either of these coming from a strong acid or strong base?
Yes.
Which one?
Ammonia. Well, oh, okay, no. Strong.
I heard Br. HBr. So what do we call Br then? Neutral. Does Al come from a strong acid or base? No. So Al is we already wrote it. It's a weak acid. Guys, I know this is like kind of a new way of looking at it, so I know if it takes a little time, that's okay. A weak acid. So together, we have a weak acid and a neutral thing. If I put this in a solution, what is it going to make? An acidic solution. And so, that's what we're looking for. So let me look here. AlBr, here, and we can just assume the other ones will work, because this is the only one with AlBr. Okay, so we eliminated doing a ton of work. I will really quickly help you guys break down this one here. This can be a little tricky, so the tricky part is breaking it down at the right point. I found that usually for these problems, you're going to have like a long first piece and then like a small second piece. So if you're trying to figure out where to break it, you're probably going to want to break it at the end here. Here, NO3 is negative, and this part is positive. Positive things. Say it together. Positive ions act as what? That's right. Weak acids, and negative ions act as what? Perfect. Do either of these come from a strong acid or strong base? Which one? NO3 comes from HNO3. So it's called? Perfect. So what is this form? Acidic, basic, or neutral? That's right. If I have an acidic piece and a neutral piece, the acidic piece, and that's right over here. Any questions about that? This will probably show up in your ACS. That's why I'm really focusing in. And I know that most of you guys are probably going to get it wrong if I didn't go over it, because I know a ton of you guys, it's a really hard concept, okay? I understand. That's why I want to spend time looking at it and making sure we can do it. Yes. I was going to get to those at the end, but let me show you guys right now. Make sure you know these strong acids and strong bases. Mm-hmm. Let me take a look. NH4F. So here, this is a tricky one. So for this one, both of these are actually coming. Here, weak acid, weak base. Neither of these actually come from a strong thing. So based on that one, I have a weak acid and a weak base. Do you guys know which is going to be more important right now?
The F, because it's an acid.
Actually, there's no way of knowing. So for you guys, when I wrote this problem, I noticed that like later, and I haven't changed it yet. But do know that if you end up with something where it's a weak acid and a weak base and they're both balancing each other out, you can't actually know if it's going to end up being acidic or basic unless you have their K values. But I don't think you guys are going to have to worry about those kinds of problems. This was my mistake. So when I wrote this, that's what I did. I ended up making a mistake in thinking, oh, of course that comes from something strong or weak. But here, so just ignore this one for now and make sure that you know how to do these. This was a mistake though, so you're not going to have to worry about balancing which is more important, weak or basic. It's always going to be either one's neutral, one's acidic, one's neutral, one's basic, or they're both neutral. It's not going to be fighting each other. Okay, so don't worry about that.
Okay.
For this one, make sure you guys remember acids do what? Donate or accept hydrogens? Acids donate, bases do what? Accept. So when I look at these pairs, if I look here, HSO4 and SO4, this guy donated a hydrogen because it has one less hydrogen. So this has to be the acid. And if I look here, looking from here to here, I gained a hydrogen. So this guy has to be the base. And then I just do the opposites of conjugate base. And this is going to be my conjugate acid. Okay, base conjugate acid, acid conjugate base. Okay? Make sure you guys look back and remember how to do that, so take some time with that. Really quickly, this is asking what is the conjugate base? These questions, it tricked me up for so long until I found a really easy way of thinking about it. If it's asking for the conjugate base of that thing, what is that thing? It's an acid. I'm asking for the conjugate base. That means the thing I'm starting with is an acid. Remember, it's acid conjugate base. They like flip. Base conjugate acid. Okay? We'll talk about it in just a moment, but I think you're right. So if this is an acid, what do acids do? Donate or accept? Donate. So let's find the one where this guy donated, and that is? You said it's Cyan? That's B here. One less hydrogen. That means that this is the conjugate base. Okay? So because this guy was an acid, we're looking for the conjugate base. That means this is an acid. Acids donate. So I try to look at how acid donating to get to the conjugate base right here. Okay? So we just look at what the thing is and think, what does that thing do? Does it donate or accept? And go from there. Here, find the pH. This is, find the pH of a HNO2. Remember, guys, finding the pH of a strong acid or base isn't super difficult, because all we have to do is look at the concentration and directly put that into the negative log. It's kind of like a really direct method for strong acids and strong bases. But what about finding the pH for weak acid or base? What do we do? Ice table. I heard Henderson. When do we use Henderson-Hasselbalch? Buffers, that's right. Buffers are Henderson-Hasselbalch. But whenever we're trying to find the pH of a weak acid or a weak base, you use an ice table. I'm going to really quickly ask if you guys could go ahead and start filling out the review. I'm just going to keep talking to you for now and kind of showing you how to do the problems. But go ahead and start filling out the review, because I need to have as many of these as I can. Can I really quickly see who does not have reviews? Can I just see hands for this table? So I see 3. I'm just going to go table by table and ask. So if you don't have it, I'll come to your table. So here are 3. Could you guys pass these down? Let me see. There's actually a session number I think you guys need to use. Okay, so let me see. Oh, here it is. So guys, the session number is session 77. So if you look here, it says bubble in. It says bubble in the number provided by the facilitator, and it's 77. So guys, bubble in 77. And don't worry, I'm going to come around to give the review out to you guys. So this table. Do you guys have reviews? Okay, so Kasia and Demi, you guys need reviews. Here you go. Okay, thank you very much. What about you guys? Anybody from this table? Yep, 1 review here.
I'm almost done.
Great, yeah, take your time. And what about this table, guys? Anybody need reviews? You guys got some? What about you guys here at this table? Good? Everybody else good? Okay, so keep working on those. I'm going to give you guys a few minutes while we're doing that, I'm going to break down this problem. But don't worry, I'll make sure to do it so you guys can also do the reviews. So take your time. So don't worry, keep working. I'm just going to keep talking to help you guys think. We said that finding the pH of weak acids and weak bases, we need an ice table. And it's just like the ice tables we did before. Okay? You solve it out. Remember, I said we can always assume that x is small. So don't waste time checking x. Always cross out that x and just solve for the x up here. So get rid of the x, assume that x is small. If you guys don't remember what I'm talking about, look back in the textbook, look back at your notes, and double check what the assumption we could make about x being small sometimes, because it saves us a ton of time and work. So once I do that, I plug in my K value, my Ka from up here, and same thing, products over reactants. I just plug everything in and solve for x. My x value is the same as the equilibrium concentration of H3O+. So remember that negative log of H3O+ gives me the pH. So I just solve for x, take my x, plug it into negative log, and out comes my pH. Okay? So, and that's answer choice B. Okay, so if you're done with the review, if you wouldn't mind just passing it along to the end of the table. If you're still working on it, that's okay. I'm going to give you a little bit of time at the end while we're asking questions. Okay, again, because we're a little short on time, I'm going to talk over these problems, but I'm not going to work it out right here. I have it worked out. In the past, I just skip problems usually and say work on it on your own, but this time I wrote it out so I could at least talk over like every problem with you guys. So for this one, what is the pH of a buffer? That should bring up what kinds of equations? Henderson-Hasselbalch, which is pH equals pKa plus the log of base over acid. Don't forget, pKa, you can get that from Ka. What do you have to do though? Negative log of Ka gives me pKa. So make sure pKa is always going to be a really nice small number. Ka is almost always going to be a really terrible long number. So if you see a big old long number in Henderson-Hasselbalch, you probably forgot to convert to pKa. Okay, so here I'm getting my pKa, which is 4.19, and I'm just plugging in base over acid. The trick here is, remember guys, buffers are made from conjugates. So they should look very similar. They should only be different by one H. That's what conjugates are. So here, we're always going to have one with an H in front of it, and probably the other isn't. Or one's going to have more H's, and one's going to have one less. So, which one is our acid, and which one is our base?
The Na.
Okay, so acid is what? What does it have in the front? H. It's either going to be the one with only H in the front, or it's going to be the one with more H's. That's our acid. Our base is the other one. Don't get tricked up, guys, by the Na in the front. If you look here, C7H5O2 and C7H5O2, these are the conjugate pieces. My Na, that's added in just to balance out the negative charge. Na, don't get tricked up and think, oh, it's not a conjugate because there's a random Na there. You might have a random Na or just a K or an Li in front of the base just to balance out the charge. It's still a conjugate though, so it can sometimes be a little trickier to recognize conjugate pairs because of that in the front. But don't forget Na, Li, and K just are in the front to balance the charge. Yes, Karina?
This is the hardest we're going to get on the ACS.
No, I'm about to show you the next one, which is a little harder, but hopefully not too hard, because I'm going to show you guys a good trick.
Okay.
If you guys have come to my tutoring sessions, you will have seen that when anytime I say buffer, I can always use the Henderson-Hasselbalch. If you guys look in your book, you're going to see that sometimes I'm given a buffer problem, but they say, what's the pH after adding some acid or some base? And usually you have to go and do like a BAC table or like an ICE table thing and figure out what the new concentrations are. I'm going to show you guys a really fast trick. Remember this, anytime you see a buffer, Henderson-Hasselbalch, no matter what. The one modification is when I'm saying that I'm adding some amount of acid or base. Here, remember that Henderson-Hasselbalch is base over acid? If I say that I'm adding something like HCl, is HCl an acid or a base? Acid. So which part do you think I should add to? The acid part or the base part? Acid. The acid. So here, if I'm adding an acid, I just add those moles to the acid part, and I take those moles away from the base. That's right. Here, what was that?
It doesn't really matter if it's strong or weak. You just need to add the acids together in this.
So the question was, it doesn't really matter if it's strong or weak, right? And the answer is, you guys aren't going to see weak acid or bases added because you guys don't know how to work with those yet. You didn't cover that in your chem book. You only added in strong acids and strong bases. You might not have realized it, but that's what happened. And here, whenever it's adding in a strong acid or strong base, if I add the acid, I just add those moles to the acid side, take them away from the base. If I add a base, what do you think I do? Add to the base, because I'm adding base, so add to the base, and take away from the acid, okay?
So that's a neat trick we can learn.
That's a really neat trick you can learn. And don't forget though, you're gonna wanna have them in moles. Usually they give it to you in moles, or they say like molarity with 1 liter, and this is gonna be the same as moles. But don't forget, they might try to throw in a tricky thing and make it where the moles are gonna be a little different. So just make sure you have it in moles. Otherwise it's gonna give you slightly up or down to your answer, okay?
Excuse me.
Yeah.
So if it's a weak acid of a solution when like 20.02 moles of like a H2 is added, you do the same thing?
If it's a weak acid or base, so the answer is you're not going to see a weak acid or base.
On the ACS?
No, or really you guys haven't seen it in Chem 2 either.
Thank God.
Okay, so don't worry about that. Okay, so this question, it asks about which of the solutions it has the greatest buffering capacity. There are 2 things that make a good buffer. Can you guys tell me one of those things?
Yeah, I know.
Okay, so I heard someone say something. This is actually the most important thing. It's right, Skyen. It has to be a weak acid and its conjugate base, or a weak base and its conjugate acid. Both those things have to be weak. If you see something strong in a buffer, there's something wrong, okay? So that's the first step. But there are 2 things once you have 2 weak molecules making a buffer. There are 2 kind of properties that make buffers good buffers. What's one of them? Equal concentration. So you want their concentrations or amounts to be as close together as possible. And what's the other thing? High concentrations. So the higher the concentrations of the acid and base, and the closer those concentrations are together, are going to make the buffer better and better. And if you look here, answer choice B has the highest concentrations that are also the closest together. Okay? So make sure you guys can do that problem as well. Make sure you understand those concepts. Here I'm going to skip 28 because we don't have enough time. And I'm going to skip 29. But let me show you guys really quickly. Again, 29, it says molar solubility. And it's kind of like an ice table, a little different, because for molar solubility, you're taking a solid and breaking it down. And so for molar solubility, the solid in the beginning is not included in equilibrium. Because you guys remember, what were the 2 things not included in equilibrium? Solids and, that's right. So we have a solid and we break it down into its pieces, into its ions, and just here, do it pretty much exactly like an ice table. And we just change, instead of X, we use S to keep track of, to help us remember that S stands for molar solubility. Okay, so you could use X and it'd still work, but S just helps us remember that when we solve for that value, it stands for molar solubility. So pretty much, the goal of this problem is to solve for that S, just like we would solve for X. For this one, don't forget, guys, this is an important equation to know. It's really easy to use. Just make sure you guys remember it. And don't forget, here, it's already negative. So if you have a negative number, you have negative times a negative, which makes a positive. This question could be tricky enough where it has like one answer that's positive, one that's negative. And a lot of students might get tricked by that because they might forget that there's already a negative here. So if the delta H is also negative, negative times a negative makes positive. Okay? So the answer should be positive. And here, it's answer choice C. And for this one as well, give me a sec. Sorry, I'm losing my voice. I'm trying to hold on to it. Okay. This one says calculate delta G and determine if it is spontaneous. So, here, remember that delta G is equal to delta H minus T delta S. What does delta H stand for? Enthalpy. What does delta S stand for? Entropy. Which one is Which delta H is favorable, negative or positive? Negative is favorable for spontaneous reactions. A negative, and that's exothermic. Which delta S is favorable for a spontaneous reaction? Positive or negative? Positive. That means an increase in randomness and an exothermic reaction are both things that are favorable for a spontaneous reaction. That means that if you have both those conditions, you're definitely going to have a spontaneous reaction because they're both favorable. But don't forget here, when you solve this out, when you plug in the values, if your delta G is less than 0 or negative, is it spontaneous or non-spontaneous? Spontaneous. Delta G less than 0 or negative is spontaneous. Now say it together with me. When delta G is positive, it is non-spontaneous. It's so easy to mix this up, guys, but this is a pretty straightforward question if you just remember it and make sure to have it in your head that negative is spontaneous. So when I solve this out, I get, give me a second, here I got this value here and it's positive. And positive means what? Non-spontaneous. This is definitely a question you could get on the ACS. In fact, I actually had this, oh no, this was from the book. So, here, positive is non-spontaneous. You could, though, have gotten this answer and forgotten that positive means non-spontaneous, and you would pick A. But you see that the only difference is spontaneous versus non. So make sure you guys remember that negative delta G means? That's right, perfect. And here, this question, it's asking for us to calculate the delta G, or free energy change, using a bunch of delta G values from the products and reactants. For this question, remember that to find the delta G, we just take the products, the value for the products, so H2O right here, and multiply it, H2O2, there we go, and multiply it by the number of moles, 2. And then subtract from that the values for the reactants. Here, H2O is negative 228. It's kind of, it might be similar, but it's not based on Hess's law. But you guys see here, products minus reactants, multiply by the number of moles, okay? That's if you're given a bunch of values and you're trying to find the free energy, and you're given the values for each product and each reactant. You just kind of put them together, products minus reactants. You can actually do the same thing for things like delta S and delta H. Okay, I want to, oh, okay, great. Yeah, you're exactly right then. And for this one then, so this is kind of similar to that equilibrium one we did earlier where we were given some reaction with some equilibrium constant, but then we had to change it up. We had to flip it and multiply by 2 to get to another reaction that looked the same, so we could find the new value for K. This is kind of similar. It says determine the free energy change in the following reaction, and it has this reaction, and we're given 2 other reactions with the free energy change. So, here I need to find how can I manipulate these reactions to look like this one here. Just recently, I had a lot of students come to me telling me that this was really tricky because sometimes you're working with 3 different reactions and you're trying to figure out how to change each one and how to add them together to get a new one. It can be really tricky. So when I took this, I kind of found a really awesome method that works really well. And that's just going one by one. Starting with the reactants and going all the way to the end, to the products, you just look at the first thing and look at where you can get that from. So here, H2O, it's a reactant. This is my target reaction. I'm trying to find the delta G of this guy. So where can I find H2O in these reactions? Which one? The second one, yeah. Tell me, Here it's a reactant. What is it in this? Okay, is that going to work out well?
No.
So what should I do to that one? Flip it. You guys see? So I'm going to say flip. Okay, so I need to flip this. Now let's go. Sorry, my voice is going. I'm going to try to hold on. Don't worry, I'm almost done. Okay, I'm going to try to talk a little quieter and into the mic. Okay, so O2. Where can I get O2 from? Either one, that's right. Don't forget though, we flip this guy, so O2 is going to be on this side. Okay, so we'll look at this later. Let's just move forward to the next one. We could get it from either one. What about H2O2? The first one, yeah. Here, it's only in the first one. So, do I need to flip this one? No, but I might need to do something to it. Look here. How many H2O2s do I have? And how many do I have here? 1. So what do I have to do? Multiply by 2. Okay, so if I multiply by 2 here on each one, and I flip this guy, I'm going to flip it out for us. Here, 2 H2Os give us 2H2 plus O2. Here, if I add these together, here I'm going to cross this out because we don't need this one. Here I'm going to get my 2 H2Os over here, H2O2s. I'm going to get my, let me look. Remember, I'm going to get my O2 to cancel, but here, how many O2s do I have up here? I have 2, so if I cancel 1, I've got 1 left, which is good. I want 1 left here. And then here, I'm going to get my H2, 2 H2s, and over here I've got 2 H2s. You guys see how these are on different sides? What can I do with these? Cancel those. Do you see any H2s in here? No, so that's what I want. So far good. And the last thing is the 2 H2Os. Put that here, and that's what I have here. So now that I know that the reactions are changed the way they need to, the thing I need to do now is just apply those changes to the numbers here and add them up. So here, 2 times this value. I'm going to flip the sign on this to a positive and add them together to get 246. Okay? So I just multiplied this by 2 and flipped the sign to positive here to get the 246. And I add them together. This is very, very different from my equilibrium. Because remember, when I flipped the reaction, did I flip the sign?
Yeah.
Actually, no. With my equilibrium, my K, when I flipped the reaction, I did 1 over. And remember when I multiplied it by a value like 2 here, I didn't just multiply the K value, I did what? Raised to the power. And when I added, you guys didn't see this, when you add the K values together, what do you do? Or when you add the reactions together, do you add the K's together? What do? Multiply them. So don't forget that K, when you manipulate those reactions, you're going to have a much different effect when you're comparing it with delta G. Okay, remember with K, if you flip it, it's 1 over. When you multiply by some constant, you raise that constant to the power. And when you add the reactions together, you multiply the K values. This is way easier. It's way more direct. You multiply, you just multiply. If you flip the reaction, you just flip the sign. And if you add the reactions together, you just add the numbers together. Do you guys see the difference there? Okay, make sure you know how to do those, okay? It can be easy to get them mixed up. Okay, we have about 5 minutes. I want to show you guys how to balance this reaction, okay? But I first want to say that the way I'm going to show you guys, if you want more practice, you can find more on how to do this at Khan Academy. Okay, who here has heard of Khan Academy? Can I see hands? Okay, if you haven't, look up Khan Academy Balancing Redox Reactions, really anywhere online. It's going to show you a really easy way of doing it. Usually when I learned this, I learned it to look at the oxidation states and just like count how many electrons would transfer and then use that to balance out the electrons. But there's a way of doing it where you just look at charges. You don't even have to assign oxidation states. And it's way easier. So look up Khan Academy Balancing Redox Reactions to learn how I'm going to show you this way of doing it. When I do this, I am going to show you guys how to assign oxidation states, just so you know how, but that's actually not required for this method of balancing redox reactions. Okay, so again, Khan Academy Balancing Redox Reactions, you guys are going to see a really easy way. Before we do that though, I want to really quickly show you this problem because my professor said it's been on every single ACS exam that he's ever seen. So, and it was actually on mine, so he was right. I don't know if they still do it, but I show students it every year. I've never asked if it was on, but it's good to know just in case. The question is, which of the following set of values are characteristic of a spontaneous reaction? Okay, the first thing we need to think about, so here it's talking about K, delta G, and E. So first, we just talked about delta G. Which value for delta G gives us a spontaneous reaction? Negative. That's perfect. So let's see here. I know delta G needs to be negative. So can it be A? No, it says positive here. Can it be B? It could be B here because delta G less than 0, that's negative. This one as well. What about here, D? No, so I just eliminated 2 out of the 3. Guys, just know that it might be just a balancing act for the ACS. Like some of the questions, you might not know how to do them at all, but you know a couple pieces. And you could eliminate maybe 2 or 3 out of all the problems and save yourself like huge percentage points on your grade because you were able to guess the right answer from eliminating most of the wrong answers. I don't know if you guys learned that like on the ACT or SAT, but it's really helpful and really boosts your score. So treat the ACS like that too. Don't just randomly guess if you don't know it. Try to think of every possible thing that you can to help whittle down those problem choices. Okay, so remember guys also, some of you guys might not remember this. This is a little bit, I think a lot of people remember this less, but for the E value, which E value gives us a spontaneous reaction? Not the same choral response for sure. Okay, so anybody? I think I heard one person. Greater than 0, positive. So I'm going to ask it again. Everybody say it together. It's positive, okay? Which E value gives us a spontaneous reaction? Perfect. I'm having to say it so we remember it when we take the ACS. Okay, so here we already know it's not this, so let's look at the remaining choices. Here this shows negative, and that shows negative. Is that what we want? No. So if I just remember those 2 things, there's the answer. I will tell you guys the last one though. K value. Remember we said it earlier today. Small k favors what? Reactants. Big K favors products. That's exactly right. So, but remember I said it's really though if K is greater than 1 or is products, and if K is less than 1, reactants. But you could think big K, bigger than 1, little k, less than 1. Okay, and here it's big K or K greater than 1 means we're favoring products. And think about it, that's what spontaneous reactions say. They say that it is going to go from reactants to products. That's what a spontaneous reaction means. It will go forward to products.
Is the Nernst equation going to be on the ACS?
I don't know. There might be a way, so the question was about the Nernst equation. I don't know all the equations that'll be on the ACS, but I do know that you have the integrated rate laws. Yeah, I see a question. E, guys, E is E cell. Remember E cell? What's the equation for E cell? Cathode minus anode. Okay? I'm just about into question time, but I really quickly want to show us how to do this, okay? So here, I'm really quick going to show you guys how to assign oxidation states. I'm going to try to get through balancing this. Actually, you know what? I have it mostly done there, but I'm going to see what I can get through here. So, rule number 2 of assigning oxidation states, don't forget there are 5 rules, make sure to go over them. Rule number 2 says that anytime I have some kind of ion all by itself, not attached to a compound, the charge that it has is the same as the oxidation state. So what's the charge on that guy? So what's its oxidation state? -1, perfect. Okay, I'm going to skip forward to here. Same deal here. I have an ion all by itself. It's got a charge of 3+. What's its oxidation state? Perfect. The last one here, what is that, I2?
0.
Why? Okay, so rule number 1 says, if I have a free element, its oxidation state is what? 0. The question is, though, what is a free element? And the answer is, free elements are, first of all, made of one type of element. So here, I2 is just made of 2 I's. It's the same element. So that's the first thing. Free elements are made of one type of element. The second thing is free elements are uncharged. So anytime you see something uncharged, made of one element, that is our free element, and its oxidation state is what? 0. Perfect. 0. Oh. Okay, here we go. 0. And here, remember that rule number 3 says, anytime we have a compound, we can break up the compound, and we can add up the oxidation states of every atom and set it equal to the charge of the compound. Okay? And rule number 5, what does rule number 5 say about oxygen? Yep, -2, not always. It says most of the time. Remember that the rules are based on, they have a particular order, and some rules are more important than others. Okay, so there are some problems where oxygen might actually not have an oxidation state of O of -2. And it's all based on the other rules, the rules above it. Rule 4, 3, 2, and 1. Yeah, Karina?
It's like peroxide, like, which is like O2, then it has like an oxidation state of 1.
I see. I think Hampton mentioned that. Yeah, that's a little piece that Hampton added. I don't know where that is it isn't from the book, but that, if you guys remember that too, then that'll definitely help you, I think. Positive. Okay, so now I'm going to solve for the oxidation state of the other one, and it's +6. So that means that here this guy's +6, and oxygen has -2. Okay, this is just assigning oxidation states. Okay, but remember, if you look on Khan Academy, you can find a way to do this without using any kind of assigning oxidation states. I'm going to really quickly show you how it looks. So the way that you can balance a redox reaction really fast is by doing the same thing as always. Just break it up into half reactions. Okay, so you just look at what matches and put them here. Cr3+. Okay, the next step is you always balance by mass of the atoms that aren't O and aren't H. So here, we have 2 I's here and 1 I here. What do we need to do? Yeah, multiply by 2. And here, 1 chromium, 1 chromium. So we're good here. Now we need to look at oxygen. Okay, here, no oxygens. On this side I have 4, on this side I have none. What do I need to do? Add 4 water. So you add 1 water for every oxygen you're missing. Now, the last step is hydrogens. So, how many extra hydrogens do I have on this side? 8, so how many do I need here? Yep, so I'm just going to add 8 H+. The trick I want to show you guys is this. Next step is you're going to add in your electrons, but the way that you can do it, if you look on Khan Academy, it'll show you, remember, electrons are negative. So what you do is you look at the charge on both sides of the reaction. So here we have a charge, I'm saying charge of here, not oxidation state, it's just like the charge of the atom, of the compounds. Here, what's the overall charge over here? 2 negatives. So I have 2 negatives over here. And here, what's the overall charge of this guy? 0, because there it's uncharged. Where do I have to put my electrons to make these charges match? On the right, yeah. Here, if I add 2 electrons to E minus,
That's oxidation.
yeah, and I'll tell you guys how to know that in a sec. Here, 2 negatives are going to add in those 2 negatives and make these guys match. So the trick is, add the electrons to the more positive side. Here, if we look here, we've got 3 pluses here and no charges here. So here, this is 3 pluses. How many positives are here? 8. How many negatives are here? 2. So what's the net charge on this side? 6 plus 6. Remember I said add them to the more positive side? Which is more positive? The left side. How many electrons do I need to add? 3 electrons. This is much easier than the other method of looking at the oxidation states, comparing, multiplying them sometimes, sometimes not. Okay? So look on Khan Academy to get a better understanding of how to do this for more practice. But this is a quick review. Don't forget the next step is to make the electrons match.
Yeah.
So here, 2 and 3, both of those can divide into 10. 10 is the first number where 2 and 3 divide into. So here, I'm going to multiply this reaction by 3, this one by 2, to end up getting, oh, I'm so sorry, I said 2 and 3 is into 10. I meant 6. So 2 and 3, the first number that they divide into is 6. Sorry, not 10. Here, so I get 6, so I multiply by 3 here, and I multiply the whole reaction by 3, and I multiply by 2 here, where the 3 electrons were, and now I multiply the whole reaction by 2, and then I just add them together, and that's the answer. Karina mentioned something. She said that here, this was oxidation. Okay, so the way to know, there's a little trick here. Here, if the electron is in the product, is on the product side, so electron on product side, that means it's oxidation, the O here and O here. If the electron is on the reactant side, it is reduction, R here and R here. So you can look at this guy here and this guy here and say electron on the product side, so oxidation of this guy, the reactant. And you can say the electron is on the reactant side, so it was reduction of the reactant. Okay? If you need more time looking over that, that's okay, but for now, that's like a quick review of that. We have just a couple minutes left. You could, okay, oil rig is oxidation is loss, reduction is gain, but that doesn't tell you which side of the reaction necessarily the electron's on. Okay, so you use both to remember oxidation is losing an electron, reduction is gaining an electron. Okay, so we have just a couple minutes left, so I will be up front for just a couple more minutes to answer any last minute questions. I'm going to leave these 2 review sheets out on this table. You guys can look through and get the answers from them, some of the worked out stuff. Okay, so I'm going to leave these here. And also, if you guys wouldn't mind gathering up the reviews when you're done and just giving them over to me, okay? So